Good morning, students. I am Suneetha, Assistant Professor of Chemistry from KGC Hanamkonda. Today, we are going to discuss about second unit of first year BSc, first semester, that is organic chemistry. In the organic chemistry, we have two topics. One is structural theory in organic chemistry, and second one is acyclic hydrocarbons. So, we are going to discuss about alkenes. Hydrocarbons which contain at least one C double bond. C double bonds. The general formula of alkenes is C and because of their nature to form oils. That is, most of the oils are olefins. Because of that reason, they are called olefins, oil forming. Olefins means oil forming. So, IUPAC name of this compound ends with "-ene". Alk is general root word and "-ene" is the suffix used to represent C double bonds. The total dissociation energy of double bond in alkenes is very high, that is around 163 kilocalories, and the bond length of C double bonds is 1.34 angstrom units, which is shorter when compared to C single bonds, that is 1.54 angstrom units, whereas that of C double bonds is 1.34 angstrom units. This indicates C double bond C bond length is less when compared to C single bond C, or C double bond C is shorter in length when compared to C single bond. The carbon atoms at double bonds are sp2 hybridized and having bond angle of 120 degrees. The shape of the molecule is trigonal, planar, or triangular planar according to sp2 hybridization. And generally alkenes, they undergo addition reactions because of the presence of the pi bond. Whereas alkanes, they undergo substitution reactions. In the case of alkenes, they undergo addition reactions due to the presence of one pi bond. Let's discuss about the different preparation methods of alkenes. Three preparations for alkenes. The first one is dehydration of alcohols. Second one is dehydrohalogenation of alkyl halides. And third one is dehalogenation of 1,2 dihalides. So these are the three preparations of alkenes. The first one is dehydration of alcohols. Now let's discuss about these preparations one by one. The first one is dehydration of alcohols. So what is dehydration of alcohols? Let us see. Dehydration of alcohols is the very common method for the preparation of alkenes. So most of the alkenes are prepared by this method, that is dehydration of alcohols. Then what is dehydration? D means loss, hydration means water, so loss of water. So dehydration refers to removal of water, loss of water. These dehydration reactions, we use the concentrated sulfuric acid or concentrated phosphoric acid are used as reagents to remove water from alcohols. And these reactions, they generally take place at the temperature range of 160 to 170 degrees centigrade. 160 to 170 degrees centigrade. So concentrated sulfuric acid or phosphoric acid, these are the powerful dehydrating agents. They like water like anything. Because of that reason, they remove water from any compound. So during the dehydration of alcohols, we use these reagents. Apart from these sulfuric acid and phosphoric acid, we can also use P2O5. But the temperature must be a little bit more when compared to this one. So here 350 to 400 degrees centigrade temperature is used when we use Al2O3, dehydrating agents for the removal of water from alcohols to prepare alkenes. So, alkenes are obtained by the dehydration of alcohols. In this dehydration reaction, loss of water or removal of water takes place, and to remove the water, we use either concentrated sulfuric acid or phosphoric acid at about 160 to 170 degrees centigrade. We also use alumina, that is Al2O3 or P2O5 at about 350 to 400 degrees centigrade. So these are the reagents which are used to remove water from alcohols. Now let's see the reaction, general reaction, which represents the formation of alkenes from alcohols. Here, this is alcohol. And adjacent carbon atoms H and OH are present here. Acid catalyst, that is sulfuric acid or phosphoric acid, on heating to 160 to 170 degrees centigrade. Then what happens is H from one carbon and OH from another carbon. That is from adjacent carbon atoms H and OH are removed in the form of water by this acid catalyst. Then we get an alkene. So alcohol is converted to alkene in presence of an acid like concentrated sulfuric acid or concentrated phosphoric acid on heating to 160 to 170 degrees centigrade. This is the general representation of dehydration of alcohols. So let's see some specific examples for the preparation of alkenes from alcohols. Here, alcohols, when dehydrated in presence of a catalyst like sulfuric acid or Al2O3 or P2O5 or phosphoric acid, etc., will be alkenes. So here, let's consider one example. This is general example RCH2CH2OH. P2O5 is used on heating. Then OH from this carbon and H from this carbon are removed in the form of water. Then we get RCH double bond CH2. That is, an alkene is produced. R is alkyl group. So we can prepare any alkene by this method. This is a few specific examples for the dehydration of alcohols to prepare alkenes. First example here we considered is CH3, CH2, CH2OH. That is one propanol. One propanol or one propyl alcohol. This is propyl alcohol, primary alcohol. Here we considered. How do you say that it is primary? Because this carbon is primary carbon. To primary carbon OH group is attached. Therefore, it is primary alcohol. So the carbon which is attached to one other carbon is called primary carbon. Therefore, here this primary carbon OH group is attached. Therefore, it is a primary alcohol. So propyl alcohol, one propyl alcohol or N propyl alcohol or one propanol. Here we consider this is dehydration on heating to 140 to 160 degrees centigrade around with the help of concentrated sulfuric acid. Here we got propene. OH from this carbon and H from this carbon are removed and a double bond is formed in between these two carbons. Therefore, the product obtained is CH3, CH double bond, CH2. That is, propene is the product obtained. This is one example. Our next example, let us see. This is CH3, CH2, CH, CH2. That is four carbons. Therefore, this is butanol. So this is 2-butanol we wrote. Why it is 2-butanol? Because on second carbon atom OH group is attached. Therefore, it is 2-butanol, which is a secondary alcohol. How do you say that it is a secondary alcohol? Because this OH group is attached to secondary carbon. What is secondary carbon? We said secondary carbon is a carbon which is attached to two other carbons. You can see this carbon is attached to this two carbons. Therefore, the carbon which is attached to two other carbons is secondary carbon. Therefore, it is a secondary alcohol. So here we consider primary alcohol as a secondary alcohol. So the example for secondary alcohol is 2-butanol. 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 So 2-butanol, when it is subjected to dehydration with concentrated sulfuric acid, then what happens? H2-butene. How it is obtained? OH from this carbon and H from this carbon are removed by the catalyst. Then we get CH3, CH, double bond, CH, CH. CH3, CH2, CHOH, CH3. So here H from this carbon and OH from this carbon are removed. Then we got 2-butene. 2-butene. So CH3, CH double bond, CH, CH3. This is 2-butene, which is why only 2-butene is obtained? Why not 1-butene? We get it out. Because OH from this carbon and H from this carbon can also be lost to give another product. That is 1-butene may be obtained. But here we did not get the 1-butene. That is a minor product. So we did not write. Only major product only we wrote. That is 2-butene is obtained. This we will discuss in the next uh, class. This is based on the stability of the carbocation during the reaction mechanism. So, let's consider this is tertiary butyl alcohol. Tertiary butyl alcohol, because how do you say that it is tertiary? Because the OH group is attached to tertiary carbon. What is tertiary carbon? The carbon which is attached to 3 other carbons is called tertiary carbon. Carbon which is attached to 3 other carbons is called tertiary carbon. So this is tertiary carbon. So to this tertiary carbon, OH group is attached. Therefore, it is tertiary butyl alcohol. Tertiary alcohol, which is tertiary butyl alcohol, is the example we considered here. So when this is subjected to uh, dehydration with isobutene, this one isobutene, iso fork shape like this. So butene, isobutene it is. This is another example for dehydration of alcohols. So what are the different methods adopted for the dehydration of alcohols? We have already discussed that the first one is heating the alcohol with concentrated sulfuric acid or phosphoric acid at about 200 degrees centigrade. 150 to 160, 170. It depends upon the um, reactant we started with. Okay. And next one is by passing alcohol vapor over alumina, that is Al2O3 or P2O5 at about 350 to 400 degrees centigrade. And generally, dehydration of primary, secondary, tertiary alcohols takes place in the order of tertiary is greater than secondary, which is greater than primary, which is in the stability order of tertiary is greater than secondary, which is greater than primary of carbocations. Let's discuss the mechanism of dehydration of alcohols. The mechanism of dehydration of alcohols, it resembles even mechanism. Even mechanism. So what is even mechanism? E1, E stands for elimination. Elimination. 1 stands for unimolecular. Unimolecular. So it is even mechanism, that is elimination unimolecular. In the even mechanism, CH and COH bonds are broken separately in 2 steps. Separately in 2 steps. So COH bond is broken in the first step, resulting in the formation of a carbocation intermediate. In the next step, the base pulls out the proton from the carbocation to form the alkene. So this is what happens in the even mechanism. So even mechanism takes place in 2 different steps. In the first step, carbocation is produced. In the second step, alkene is produced. Okay. Now, It should be poor leaving group, but protonation by the acidic catalyst converts it to a good leaving group. Okay. So, in the second step, loss of water from protonated alcohol gives a carbocation. So, finally, abstraction of proton by weak base such as water or sulfuric acid, the ion of sulfuric acid, that is HSO4 minus, it gives the steps where we get the alkene. So first one, protonation of hydroxyl group with the help of the acid catalyst. So this is alcohol. Here from this sulfuric acid, with the help of a pair of lone pair of electrons present on oxygen of OH group, it combines, it abstracts proton from the sulfuric acid and forms a bond with the oxygen. Then we get this compound intermediate where oxygen is having positive charge, and the rest of the ion is HSO4 minus ion, that is here. Okay. In the next step, step 2, what happens? Ionization of carbocation intermediate. Ionization to a carbocation intermediate, that is this compound, it gets ionizes to form a carbocation by the loss of water molecule. This is the slow step and rate determining step. So in the rate determining step, only one molecule is participating. Because of that reason, it is a unimolecular mechanism. Unimolecular mechanism. So in this step, this ion loses water, carbonium ion. Carbonium ion is the ion in which carbon bears a positive charge. Is called carbocation. Anion. Okay, so this is carbonium ion produced in the second step by the loss of water from this molecule. Okay, now finally what happens? This carbocation, it abstracts, it loses the hydrogen, that is proton, from adjacent carbon to this carbocation to form an alkene. To form an alkene. So this is what happens in the elimination reaction, that is E1 elimination, to form the alkene. To form the alkene. So this is known as elimination unimolecular reaction. So in this CH bond cleavage in the first step takes place. Initially what happens in the first step, what happens? This alcohol, with the help of a lone pair of electrons present on oxygen, a protonation takes place to form this ion. This protonation is because of the presence of the acid catalyst. From this acid catalyst, one proton is utilized by this alcohol. This proton, it goes and attacks this due to the presence of lone pair present on oxygen, it abstracts this proton to form this ion where the oxygen is having positive charge. In the next step, what happens? This ion, it ionizes and it loses water molecule to form the carbocation. This is a slow and iterate determining step. So in this step, only one molecule is participating. Therefore, it is called unimolecular mechanism. And in the last stage, what happens? This carbocation, it loses one proton to the base, weak base like water or HSO4 minus to form the alkene. So this is the reaction mechanism where um, alcohol loses water to form the alkene. This is elimination unimolecular mechanism. Elimination unimolecular mechanism. So in this Elimination unimolecular mechanism. The reactivity of alcohols depends upon the carbocations. The tertiary alcohols react faster than secondary alcohols, and primary alcohols are the least reactive one. Tertiary alcohols more reactive than secondary. Secondary is more reactive than primary. That is, primary alcohols are least reactive in this mechanism, we can say. So this is the order of reactivity, that is tertiary is greater than secondary, which is greater than primary. So rearrangement of carbocation intermediates are very common in the case of alcohol dehydration. Now, now let's see the E2 mechanism. Okay. Now, um, right. Now, second method of preparation of alkenes is dehydrohalogenation of alkyl halides. Dehydrohalogenation of alkyl halides. So, in this dehydrohalogenation of alkyl halides, D means loss, halogen means loss of hydrogen and halogens from adjacent carbon atoms of alkyl halide to give alkene. This is dehydrohalogenation of alkyl halides. Okay, so dehydrohalogenation is the elimination of hydrogen and halogen, loss or elimination of hydrogen and halogen from alkyl halide to adjacent carbon atoms of alkyl halide to form an alkene. So let's see this general reaction. Here, two adjacent carbon atoms. One carbon has one H and another carbon has X, that is halogen. Chlorine, chlorine, bromine, iodine. Generally, chlorine, bromine, and iodine only we consider. Fluorides are highly reactive, explosive. So here we considered this, and this loses H from one carbon and X from another carbon. Minus of HX takes place to form the alkene. And here the catalyst used in dehydrohalogenation is alcoholic KOH. It is catalyzed by a base like alcoholic KOH. Alcoholic KOH. That is KOH in alcohol. Okay. Now let us. Dehydrogenation can take place by E1 and E2 mechanisms. E1 is elimination unimolecular mechanism. E2 is elimination molecular mechanism. So, an alkene is obtained from alkyl halides. So second order elimination E2 is better method for the synthesis of alkenes. Okay. And from alkyl halides, E2 mechanism is more preferred to prepare alkenes. Okay. Right. Now let us see both the mechanisms one by one. So first of all, dehydrohalogenation by E1 mechanism. Dehydrohalogenation by E1, that is elimination unimolecular mechanism. So here the abbreviation E1 stands for the elimination unimolecular. The mechanism is called unimolecular because the rate limiting or rate determining transition state involves a single molecule. The rate determining step, only single molecule is involved. Because of that reason, it is called unimolecular. And this method usually takes place in polar solvents like alcohol or water. So, even mechanism takes place in polar solvents, that is alcohol, water, etc. can be used here. Now, generally, secondary and tertiary alkyl halides undergo elimination by this method. So, even method is more preferred for tertiary and secondary alkyl halides. So let's see the different steps involved in even mechanism. There, the step one is unimolecular ionization to give a carbocation. This is rate determining step. Unimolecular ionization to give a carbocation. This is rate determining step, RDS, rate determining step. So then the rate determining step, only one molecule is participating. This molecule, it loses X minus. X minus is lost. That is, this X goes along with this bond pair of electrons, CX bond pair of electrons. Then this carbon becomes positive. You can see here, this is a carbonium ion produced and X minus is eliminated. This is rate determining step. In this, only one molecule is participating. Because of that reason, it is called unimolecular reaction, elimination reaction. Now, next, the second step. Second step is our first step. It is the first step. A base abstracts proton from the carbon atom adjacent to the carbocation. So this is carbocation. This is a carbon atom adjacent to carbocation. From this, the hydrogen atom is abstracted by the base. So base abstract this proton from the carbon which is adjacent to carbocation, resulting in the pi bond formation. A new pi bond is formed in between the two carbon atoms because of the loss of H plus. So this bond pair of electrons, they move towards this, in between these two carbon atoms, to give a pi bond. So this is deprotonation by a weak base or solvent to give alkene. From this carbocation, this weak base, it abstracts proton to give an alkene. These are the two steps involved. So first step is this one, loss of halide ion to form a carbocation, which is rate determining step. And second step is this one, this from the carbocation, a weak base or solvent, it abstracts steps, and second step is the first step. This one, even elimination. Even elimination is generally accompanied by SN1 substitution. SN1 is substitution nucleophilic unimolecular reaction. So substitution nucleophilic unimolecular. So what is that happening here? Let's see. So in the first step, we said that this is rate determining step. In this alkyl halide, it loses X minus, that is halide ion, to form a carbocation. Then what happens? Now this B, that is alcohol, because we used alcoholic KOH as a reagent in dehydrohalogenation reaction. So this alcohol, it goes and attacks this carbocation with the help of lone pair present on oxygen. Then what happens here? Combines with the oxygen to form this molecule. And H, it goes with this X in the form of H. As even reaction requires ionization of an alkyl halide to a carbocation, this one, first step, we are talking about the first step. Carbocation intermediate, the order of reactivity is tertiary greater than secondary greater than primary. So, in this elimination reaction, in the first step, this halide ion, if it is lost, we get a carbocation. This carbocation, if it combines with the alcohol present in the reaction mixture, we will get this product. This is nothing but an ether. So this is also possible. This is generally accompanied by SN1 substitution we said. So this is also possible in this elimination reaction, we mean to say. Now in this even elimination reaction, it in this alkyl halide ionizes to give the carbocation. So the reactivity order of alkyl halides depends upon the stability of the carbocations, and we know that carbocation stability order reactivity of alkyl halides to give alkenes is also in the same order. That is, reactivity order is also same, tertiary greater than secondary, which is greater than primary. Next method, dehydrohalogenation of alkyl halides by E2 mechanism. What is E2? E2 stands for elimination by molecular. So elimination can also take place under second order conditions when a strong base is present in the reaction mixture. So in this reaction, E2 reaction, yield of the product, what is the product we are preparing? Alkene. So the yield of the product, that is the yield of the alkene, is more, that is excellent yields of alkenes were obtained with bulky secondary and tertiary alkyl halides. So in E2 mechanism, if we start with secondary and tertiary alkyl halides, the highest yield of alkene is obtained. And next, the concerted E2 reaction takes place in a single step. So E2 reaction takes place in one step, whereas E1 elimination takes place in two steps. Now let's see. A strong base, it abstracts a proton on a carbon next to the leaving group, that is halogen, LEA, leaving, it is leaving group, that is halogen, and the leaving group leaves resulting in the formation of an alkene. So the first is this is a single step mechanism we see. So in this, what happens, from the alkyl halide, a base, it abstracts a proton. It abstracts a proton on a carbon next to the leaving group. So this is the leaving group. This is attached to this carbon. So the next carbon is this carbon. From this carbon, a hydrogen atom is abstracted by a base. Then we will get a transition state like this. So here, what is that happening? This X is the bond between this carbon and X is becoming weak. Dotted line we wrote. And here, this base, as it is forming a bond with H, it is now only being formed. So the bond between this carbon and this hydrogen, it weakens. You can see dotted line here. Okay. So this is the transition state where a base is forming a bond with the hydrogen atom of the carbon, which is adjacent to the carbon to which halogen atom is attached. So this is the transition state. This is transition state is a hypothetical one, and this transition state, it loses this X minus. It loses X minus. As this base, it abstracts this proton. The pair of electrons present in between carbon and hydrogen moves towards these two carbon atoms, and this X, it goes along with the pair of electrons in the form of X minus. Thus an alkene is obtained. And here B and H, the base and this proton BH is obtained, and this X goes along with a pair of electrons in the form of X minus. So this is the reaction mechanism. This is E2 mechanism. Why it is called E2 mechanism? Because in the transition state, two molecules are present. One is alkyl halide, the other one is base. So this is alkyl halide and the base. Both are present. Two molecules are present. Thus it is known as E2 mechanism. That is elimination by molecular. And this is tertiary butyl bromide in presence of a strong base. What happens? Bromine goes along with pair of electrons in the form of Br minus, and this OH, it abstracts hydrogen from the adjacent carbon. All the three carbons are adjacent. From any carbon, hydrogen can be abstracted by the base. Then we will get this compound. So if this abstracts a hydrogen from this or this or this, we get the same product. Okay, this is isobutene is the product obtained in this reaction. So this is tertiary butyl bromide. When it is subjected to dehydrohalogenation, OH, it abstracts one proton and it forms H2O. And this Br, it goes along with the pair of electrons in the form of Br minus. Okay, now let's see the order of reactivity of alkyl halides towards E2 mechanism. E2 elimination is found to be tertiary greater than secondary greater than primary. And the reactivity order reflects the greater stability of shows that highly substituted alkenes are more stable. That only given by this order tertiary greater than secondary greater than primary. Now, third preparation of alkenes is dehalogenation of 1,2-dihalides. Dehalogenation of 1,2-dihalides. So what is dehalogenation? D means loss, halogenation means halogens. So two halogens from adjacent carbon atoms are removed in this process to form the alkene. So dihalides means two halogens are present where 1 and 2 and that is and one first carbon one halogen and second carbon is another halogen is present from adjacent carbon atoms. Halogens are removed and this reaction is known as dehalogenation reaction. Generally we use vicinal dibromides. 1,2 dibromides are vicinal dibromides. Vicinal in the sense when the two halogen atoms are present on adjacent carbon atoms, then it is known as vicinal dihalide. When two halogens are present on the same carbon atom, then it is called geminal dihalide. So here in this reaction we considered vicinal dihalide. So here we considered 1,2 dibromides, that is vicinal dibromides are converted to alkenes by the reaction with either sodium iodide or zinc dust. So the reagent used here is the catalyst or reagent used in this dehalogenation reaction is zinc dust in acetic acid, zinc dust in acetic acid or zinc dust in methyl alcohol, or sodium iodide can also be used as a reagent in this reaction. Now let us consider this. Here the two carbons 1 and 2, first carbon 1 carbon then sodium iodide. It comes and removes Br plus. This I minus it removes Br plus. Then the bond pair present in between this C and Br, it moves towards these two carbon atoms. Then what happens? This Br it goes out along with a pair of electrons in the form of Br minus. So this I minus and Br and this Na plus and this Br minus in the form of NaBr are produced. So here alkene is the product obtained, acetone is the solvent used here. Okay. In the similar way, instead of sodium iodide, we can also use zinc in acetic acid or zinc in methyl alcohol as a. Then what happens? We get an alkene and this zinc along with two bromines in the form of zinc bromide. A few points about the dehalogenation of vicinal dihalides. Dehalogenation which takes place by E2 mechanism. In this zinc acts as a reducing agent in zinc and acetic acid. First one is I minus used and I minus that is sodium iodide and zinc can also be used as a reducing agent. So dehalogenation with I minus takes place by E2 mechanism and zinc acts as a reducing agent in zinc in acetic acid. These are the different points about the dehalogenation and actual reaction takes place at the surface of a metallic zinc when we use zinc and acetic acid or zinc and methyl alcohol and zinc is oxidized from 0 oxidation state to +2 oxidation state forming ZnBr2. So if we consider metallic zinc, its oxidation state is 0. If we consider the zinc bromide, this is the product, one of the products obtained where the oxidation state of bromine is -1, therefore that of zinc is +2. So zinc in this reaction, zinc is getting oxidized from Zn to Znbr2. It is becoming, its oxidation state is increased from 0 to plus 2. Thus we can say that zinc is getting oxidized. When the zinc is getting oxidized, it is acting as a reducing agent. Therefore, it is reducing 1,2 dihalides to alkenes. So let us see the reaction. Zn gives rise to Zn plus 2 electrons. Zinc loses 2 electrons to form Zn plus 2. And this 1,2 dihalide, 1,2 dibromide, here we consider 1,2 dibromide. It utilizes these 2 electrons. Then this carbon becomes negative. This Br, it comes out along with pair of electrons. You can see this. See this carbon, it is having a negative charge and Br is lost. So RCH negative CHR Br. So this is what present here. Then this negative charge, it goes in between these 2 carbon atoms. Then this bromine, it goes along with the bond pair of electrons to form an alkene and Br minus, minus Br minus. So Br minus is lost and RCH double bond CHR and alkene is produced. And this bromide and this bromide and this Zn plus 2 combine to form ZnBr2. So this is about the reaction of dehalogenation with zinc in acetic acid or zinc in alcohol. Next, orientation of double bond in elimination. So in elimination reaction, where the double bond is formed, that the position of the double bond, that we can discuss here. So this can be discussed with the help of a rule known as the Zaitsev rule or Zaitsev rule. Zaitsev rule or Zaitsev rule. Okay, so this rule states that in the dehydration of alcohols or in the dehydrohalogenation of alkyl halides, hydrogen is preferentially eliminated from the carbon with lesser number of hydrogen atoms. Whenever an alcohol or alkyl halide is present, the hydrogen atom is eliminated from the carbon which contains less number of hydrogens, then that rule is known as Zaitsev rule, and the alkene with most substituted double bond is produced in this elimination reaction according to Zaitsev rule, and the highly substituted alkene is called Zaitsev product or Zaitsev product. So according to Zaitsev's rule, in eliminations, that is E1 or E2, where there are 2 or more possible elimination products possible, the product with most substituted double bond or thermodynamically most stable product is predominating. So the highly substituted alkene is called Zaitsev or Zaitsev's product, we said. So this we can explain with the help of an example. Let's consider this example. This is 2-bromobutane. 2-bromobutane. Okay, 2-bromobutane, when it is subjected to dehydrohalogenation with a base like KOH or NaOH, then what happens? Br minus from this carbon is eliminated. H plus from either this carbon or this carbon must be removed. So, which is to be removed and which is the major product that let us consider here according to Zaitsev's rule. So according to Zaitsev's rule, we said that when Br minus is eliminated from this carbon and hydrogen from either this or this must be removed. According to this rule, the carbon with less number of hydrogens loses a hydrogen atom, we said. The carbon with less number of hydrogens. From there, that carbon only the hydrogen is lost. So these 2 are adjacent carbons to this carbon. So this carbon has 2 hydrogens, whereas this carbon has 3 hydrogens. Therefore, hydrogen must be predominantly removed from this carbon only because it has less number of hydrogens. When H is removed from this carbon and Br from this carbon, we get 2-butene as a major product. You can see here. CH3, CH double bond, CH, CH3. This is 2-butene. This is disubstituted. Disubstituted in the sense, this is the C double bond C. And this carbon has a substituent and this carbon is also a substituent, that is more substituted double bond is obtained in this product. If we consider this product that is bromine from this carbon and hydrogen from this carbon are lost, then what do we get? We get one butane. One butane. If we consider this one butane, this carbon is not substituted. Only hydrogens are present. No substituent is present on this carbon. Whereas this carbon has an ethyl substituent. So it is monosubstituted alkene. Whereas this is disubstituted alkene. So more substituted alkene is the more substituted double bond, or most substituted alkene is the most stable product. Therefore, here 2-butane is the disubstituted alkene. Therefore, it is the major product obtained, whereas this is the minor product. You can see here 81% of 2-butane and 19% of 1-butane is obtained. So, this is about the Zaitsev or Zaitsev's rule. Now, thermal stability of alkenes is in the order of thermal stability. Which alkene is more stable? So, when the alkene, this is more substituted. That is, if we consider this alkene, 4 substituents are present. If we consider this alkene, 3 substituents are present. This one, only 2 substituents. If we consider this, here also 2 substituents, but both are the same carbon. Last one, only 1 substituent. So, when the double bond is having more substituents, it is more stable. C. Cr2 double bond Cr2 is more stable than R2C double bond CHR. That is 3 substituents, which is more stable than R and R2 substituents. Either 2 substituents are different or 2 substituents are same. All are equally stable. Okay, so here only 2 substituted alkene. Here only one mono-substituted or one substituent is present on this doubly bonded carbon. Therefore, this is less stable. So this is alkenes. So when the alkene is more substituted, it is more stable. It is less substituted, it is less stable. We come across in this topic, which we have covered today. The first one is what is its rule? Explain with an example. Just now we have discussed. And next one, give any two methods for the preparation of alkenes with suitable examples and mechanism. So, two different methods. Dehydration of alcohols we can give, or dehydrohalogenation of alkyl halides, or dehalogenation of dihalides. So, these are the three methods we studied. Any two you can write easily. Next one is give the structure and product expected from the dehydrohalogenation of 1-bromohexane. So 1-bromohexane structure you write, subjected to dehydrohalogenation, then predict the product. Let's stop our topic here. Here we discussed only preparations of alkenes, and in the next class we will discuss the properties